continuing our study of trigonometric equations. Alright, let's set up a situation here. Let's say, what if we have 2 cosine squared x plus cosine of x minus 1 equals 0, and we'll impose the following restriction that x is less than or equal or greater than or equal to 0, but strictly less than 2 pi. Alright, we want to solve for x in this situation. But notice it's not as simple as grouping like terms and taking the cosine inverse, because this is cosine squared x and this is cosine of x. All of the like terms are grouped already and there's nothing else you could do. Furthermore, the cosine inverse function doesn't travel across multiplication, addition, subtraction, or division like you'd expect. So it only works on one term. So we have to figure out how to solve this equation in this manner. We notice that this is a quadratic equation in cosine of x, because here's a squared term, here's a first power term, and here's a constant term. So what we can do is we can make the following substitution. Maybe we use t for trigonometry. Define that to equal cosine of x. Okay? T for trigonometry, define that to equal cosine of x. Then we may say that t squared is the same thing as cosine squared x. Alright? Doing this substitution into our equation implies that we get 2t squared plus t minus 1 is equal to 0. So the point of having this substitution was in order to change this trigonometric equation into an algebraic equation. Now it's an algebraic equation in the variable t, and we can solve it using the quadratic formula or completing the square or direct factoring. Okay, so I'm going to choose to complete the square. So what I'll do is I'll divide both sides by 2, so I will get t squared plus 1/2 t minus 1/2 is equal to 0. Bring the calculation over here. So then I get t squared plus 1/2 t is then equal to positive 1/2 over here when I add 1/2 to both sides. And now I'm going to complete the square in the variable t. So I'll get 1/2. I'll divide it by 2 and square it. So that's 1/4 squared, and that's 1 over 16. So I add 1 over 16 to both sides. So this becomes, I multiply top and bottom by 8, so I get 8 plus 1 divided by 16 over here. And over here, this factors into t plus 1 over 4 quantity squared. That's equal to 9 over 16. Okay, and 9 over 16, what does this break up to? Well, 9 is 3 times 3. 16 is 2 times 8. Notice that nothing cancels, so 9 over 16 is as simplified as possible. Alright, so now in order to solve for t, which in turn will allow us to solve for cosine, which in turn will allow us to solve for x, taking the square root of both sides here, now I get the square root travels across multiplication and division, so this would become square root of 9 divided by square root of 16. Well, this becomes 3 over 16, technically 3 over 4, and technically plus or minus 3 over 4. So this becomes plus or minus 3 over 4. And this just becomes t plus 1/2 is equal to plus or minus 3 over 4. Or t over 1/4, I mean, not 1/2, but t over 1/4. So over here, I'm going to delete this side. Okay? Alright? So now I get t plus is equal to when I elect to add, so that's really negative 1/4 plus 3 over 4, and so that becomes 2 over 4, which is 1/2. So this is one of our answers, is 1/2. And then t minus when I elect to subtract, that's negative 1/4 minus 3/4. This becomes negative 4/4. This becomes negative 1. So that's another one of our answers over there. Okay, so I'm going to clear up some real estate here. Alright? Now, because t is equal to 1/2 and -1, remember we had our variable t. T was defined to be cosine of x. So this implies over here that I have cosine of x is equal to 1/2 and cosine of x is equal to -1 correspondingly. Okay? Now we proceed to solve for x. So over here we take the cosine inverse of both sides. So this implies that x is equal to the cosine inverse of 1/2. And over here, when we do it here, this would imply that x is equal to the cosine inverse of -1. Okay? We will go to the unit circle in order to determine where these values lie. Clearly, this is a question that says at what angle is the cosine function equal to -1? There's only one angle that does that, and that's pi. So here, x is equal to pi plus 2n pi, because 2 pi is the period of the cosine function, okay? And over here, when is the cosine function, at what angle does it evaluate 1/2? Well, we know that that is true over here at pi over 3. And we know that that is true over here at 2 pi over 3. How did I come up with those values? Well, I know at pi over 3, it's a special angle. That's when cosine is 1/2. And then I know that at pi over 2, if I add a 30-degree analog in radians, pi over 6, pi over 2 plus pi over 6 is equivalent to 2 pi over 3. And actually, the cosine value here would be -1/2, not +1/2. All right? So actually, that is not necessarily true. What you want is actually for a positive cosine value, for it to be this angle right here, correct? So that was an error in the thinking, because over here, the reason 2 pi over 3 is not correct is because that would give you -1/2. We want +1/2. So notice this here, it's the same line of reasoning. This is at 3 pi over 2. We will add a 30-degree analog of pi over 6 to it. So 3 pi over 2 plus pi over 6, top and bottom multiplication by 3, that gives me 9 pi plus pi all over 6. This is equal to 10 pi all over 6. This is equal to 5 pi all over 3. So this angle right here is 5 pi all over 3. So this is going to be equal to pi over 3 plus 2n pi. 2n pi. And it also equals 5 pi over 3 plus 2n pi. Okay? And yeah, it looks kind of cluttered, but I will now rewrite everything here. Just delete this information here. Okay? So, let's just kind of rewrite everything we had. X is equal to pi plus 2n pi. Alright, that was from cosine inverse of -1. And then also x is equal to pi over 3 plus 2n pi. And also x is equal to 5 pi over 3 plus a 2n pi. Alright. Now we will begin to plug in values of n and tabulate which values lie within this interval between 0 and 2 pi. The values that exceed 2 pi we throw out, okay? So for n equaling 0, our outputs will just be pi over 3, 5 pi over 3. None of these surpass the value 2 pi, so they're good. Let's plug in n equals 1. Okay, so now this is going to be pi plus a 2 pi. This becomes 3 pi. This clearly exceeds, 3 pi clearly exceeds 2 pi, so we don't want that one. Now let's do pi over 3 plus a 2 pi. Notice that that also will exceed 2 pi because any number added to 2 pi is greater than 2 pi. So we don't want this one either. And let's do this one, 5 pi over 3 plus 2 pi. Again, any number added to 2 pi exceeds 2 pi. So this value also exceeds our restriction here. All right, so the only values that worked were pi, pi over 3, and 5 pi over 3. So those are the only values that satisfy this equation right here. Notice that if we were to plug in any of these inputs into this equation, we would get the output equaling to 0. I'll prove it to you. I'll do an easy one for pi. I'll replace x with pi, and if I plug it into this equation, it should end up giving me equal to 0. So then 2 cosine squared of pi plus cosine of pi minus a 1. What does that give us? Well, cosine of pi is -1, but -1 squared is +1 times 2 is +2. So we get a +2 here. Cosine of pi is -1, so this is plus a -1 minus a 1. So this -1 minus a 1 becomes a -2, so I get 2 minus 2, and that equals 0. Cha-chink! Notice that that's precisely what this equation is saying. It's saying find the values of x, that whenever you plug in those values for x, the output's 0, and we found one. It's pi. Pi over 3 also works, and 5 pi over 3 also works. You at home, go evaluate it and see it for yourself. So now that we've done this problem, let's do another problem. Okay? Still doing trigonometric equations here. Let's do something like 4 sine squared of x minus 1 equals 0. And the same familiar restriction should hold right here. Solve this equation here, okay? So we can do a substitution again, but for this one, you know, it's slightly trivial. You don't have to substitute it, or you can. Notice that if we let t to be defined as sine of x, then t squared is a sine squared of x. Then this equation breaks down to the very simple quadratic equation of 4t squared minus 1 is equal to 0. Then you can solve for t algebraically by adding 1 to both sides, and then dividing both sides by 4. And then taking the square root of both sides to get what t is. So t is equal to plus or minus the square root of 1/4. This implies that t is equal to plus or minus 1/2, okay? Because the square root distributes to the numerator and the denominator. Square root of 1 is 1, square root of 4 is 2, and we put that plus or minus here. So t plus is 1/2, and t minus is -1/2, okay? So because t was sine, that means sine of x is equal to 1/2, and sine of x is equal to -1/2, all right? We could have not even done this, okay? We could have just algebraically solved for sine squared of x. We could have just added 1. I would get 4 sine squared of x is equal to 1. Divided by 4, I would get sine squared of x is equal to 1/4. Taking the square root of both sides, and I would get sine of x is equal to plus or minus 1/4 square rooted. And so that means sine of x is equal to plus or minus 1/2. And so you'd get sine of x is equal to 1/2, and sine of x is equal to -1/2. Okay? So this substitution was not necessarily needed. It's just allows us to see this in a more familiar fashion in the way we do it in algebra, so that it's easy to do. It's not fully necessary, okay? But it is a helpful tool, a helpful trick to do for you to be able to solve the equation, because writing out sine of x, you might get confused and you might forget that you can actually switch it with just one symbol, t, okay? It doesn't have to be t, it could be any letter, any symbol, it could be Greek or any other letter of any other language. So now that we know that we've reduced to these two equations, in order to solve the problem, we just have to determine what x is in these two situations. Notice that taking the sine inverse of both sides of both of these equations implies that x is equal to the sine inverse of 1/2, and x is equal to the sine inverse of negative 1/2. Okay? For 1/2, we got to think about this in terms of the unit circle, okay? For what angles is the sine function outputting a 1/2? Well, we know that one of the special angles is pi over 6, and that the sine of pi over 6 is 1/2. So that's one of them. So this is going to be equal to pi over 6 plus a 2n pi, because the period of sine is 2 pi, and all integer multiples added to pi over 6 will make it land back in the same spot. But that is not it. There's also another one over here in the second quadrant right there. That's another region in which sine is a positive 1/2. Okay, and where is that at? Well, it's at pi scooted back by a 30-degree analog, which is pi minus a pi over 6. So notice that that makes it at 5 pi over 6. So this is also, I'll put a comma, also equal to 5 pi over 6 plus 2n pi. Okay? Similarly here for the negative 1/2, let's delete this unit circle and analyze the values at which it is a negative 1/2. Okay? Sine assumes negative values in the third and fourth quadrant respectively, and so it is going to have a negative value here and here at these very shallow angles. Notice that the sine over here is 0 and it dips into the negatives over here. Well, this is going to be at pi plus a 30-degree analog, pi over 6, which gives me 7 pi over 6. So this is going to be 7 pi over 6 plus its period integer multiple 2n pi, comma, this region right here, where is this located at? Well, it's 2 pi minus this pi over 6. That's where we would get a negative 1/2. And so notice when we do the calculation, this becomes 12 pi minus a pi all over 6, which reduces to 11 pi all over 6. So this becomes 11 pi all over 6 plus 2n pi. Alright, so we've solved for x in general here. What I have in the box down here in this bottom right corner is what our x's are. It's those values that we've highlighted. Okay, so now that we know what x is in general, what do I mean by in general? I mean, this is a general notation for all the values. Now we gotta find the explicit values that lie within this range. Explicit means don't have symbols like n, actually plug in numbers for n. So when n is equal to 0, we find some explicit values. We find pi over 6 as an explicit value. We find 5 pi over 6 as an explicit value. We find 7 pi over 6 as an explicit value. And we find 11 pi over 6 as an explicit value. Alright? Notice that none of these values exceed 2 pi. So we continue excavating and we continue extracting more solutions to this equation. Next, we're gonna set n equal to 1. So now I get pi over 6 plus 2 pi. So any number plus a 2 pi exceeds 2 pi, so that doesn't work. Over here I get 5 pi over 6 plus 2 pi. Any number added to 2 pi exceeds 2 pi, so that doesn't work. Same here for 7 pi over 6 plus 2 pi. Same here for 11 pi over 6 plus 2 pi. So notice that after n equals 0, I'll be adding a 2 pi to all these non-zero values, which will cause it to exceed 2 pi. The output will then exceed 2 pi. Because if you add anything to 2 pi, it's now over 2 pi. Okay? And that would be over the restricted range of 0 to less than 2 pi. So all the values for n equals 1, and n equals 2, and n equals 3 will fall outside of our restricted domain. And so we won't use those. So we found the answers. It's pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Those are all of our answers. So we've solved this equation. If you recall, we solved this equation 4 sine squared x, I believe it was minus 1 is equal to 0. And all of these are solutions to this equation. So for instance, we'll plug in that first value, pi over 6. Notice that 4 sine squared of pi over 6 minus 1. Once we do this calculation, it should equal 0. If it is a bona fide solution to this equation, this should equal 0. Let's see. Well, this becomes 4 times sine of pi over 6 is 1/2, and 1/2 it goes in here, and then it's got to get squared, okay? Because it's a sine squared, so it's 1/2 squared. So then that becomes 1/4. So this reduces to 4 times 1/4 minus a 1. Notice that 4 times a 4th is 1. And so we have 1 minus 1. And we all know 1 minus 1 is equal to 0. So it is in fact, this is in fact a solution to that equation. And so this is what we're doing here. We're finding roots to a trigonometric equation, whereas before you guys were finding roots to an algebraic equation. But these trigonometric equations can be treated as algebraic equations, as you saw in this video.